megahertz SAW guides one sphere into each cavity.
All right, let's jump right into something that sounds like it's straight out of a sci-fi movie, but I promise you, it's very, very real. We're talking about fishing with sound, using sound waves as these incredibly delicate tweezers to grab and move things you can't even see.
I mean, just think about that for a second. How do you possibly trap something you can't even see? We're talking about nanoparticles here, things so tiny that the random vibrations of molecules around them, just the normal chaos of the universe, can send them flying off in any direction. How in the world do you get a hold of just one?
And that, right there, is the nanoscale challenge. Being able to precisely control these individual particles, it's one of the biggest hurdles in modern science. It's the kind of problem that, if you solve it, you unlock huge advances in medicine, in engineering, you name it.
So the old way of doing this involves stuff like ultracentrifugation, basically spinning things really, really fast. But it's kind of like using a sledgehammer for a delicate task. It's slow, it can actually damage the samples, and you're definitely not getting that perfect one particle per well precision that scientists are after. But now, there's a new promise on the horizon. Something fast, incredibly gentle, and unbelievably precise.
And this is where it gets so cool. This new promise, it's all about going fishing with sound waves. Forget any kind of physical tool. The idea here is to use pure sound to pluck nanoparticles out of a solution.
And just to give you a sense of the scale we're playing with, the particles they're controlling here are just 300 nanometers wide. For a little perspective, a single human hair is about 80,000 nanometers thick. So yeah, we're operating on a level that is almost impossible to wrap your head around.
And listen to how the researchers describe it. It's so elegant. They say the particles, these little spheres, they just slide as if they're pulled into each little hole, one per cavity. There's no force, no violence, just this gentle, perfect placement. It really captures how amazing this technique is.
So what's the magic here? How is this even possible? Well, the secret sauce is a technology called surface acoustic waves, or SAW for short. And we're going to break down exactly what that is.
All right, let's pop the hood and take a look inside this acoustic trap. How does a simple sound wave transform into a pair of nanoscale tweezers? It's pretty genius. First off, what even is a surface acoustic wave? The best way to picture it is like a ripple moving across the surface of a pond. Except instead of water, it's a super high-frequency vibration, like a microscopic earthquake traveling across the surface of a solid chip. Okay, so here's how it works, step by step. First, a surface acoustic wave is sent across a chip. That wave passes underneath a tiny channel that's filled with a fluid containing our nanoparticles. Now here's the really clever part. The bottom of that channel is lined with this film that has thousands of tiny little pits, or nanocavities. As the sound wave zips by, it makes each of those little pits vibrate, and that vibration creates a tiny, stable vortex of pressure, a perfect little well that just gently sucks in and holds on to a single nanoparticle.
And, this is a huge deal in physics. See, at this tiny scale, particles are constantly being slammed into by water molecules, just bouncing around randomly. It's called Brownian motion. It's pure chaos. The fact that these gentle sound waves can create a force that's strong enough to overcome all that chaos and hold a particle perfectly still, that is a massive, massive achievement. So trapping a nanoparticle with sound is incredible science for sure. But so what? Why does this matter in the real world? Well, let's talk about the applications, because this is where things get really exciting. First up, let's head into the doctor's office, because the potential impact on medical diagnostics is just enormous. Imagine you could take a simple blood sample, and without adding a single chemical or antibody, you could perfectly separate out these tiny things called exosomes. They're critical biomarkers for diseases. This tech could create these dense, perfect arrays of them, ready for analysis almost instantly. We're talking about the potential for much faster, more accurate diagnoses for all sorts of conditions. Okay, next stop. Let's go over to the materials science lab. This is a field where precision is absolutely everything. So you can use this exact same acoustic technique to arrange catalyst nanoparticles into perfect, uniform grids. Now, why would you want to do that?
because it turns out the exact distance between these catalyst particles can totally change how fast and efficient a chemical reaction is. This gives scientists a level of control they've basically only dreamed about for creating better, more efficient materials.
And if we look even further down the road, this technology could be a fundamental building block for the next generation of super advanced sensors.
Think about it. You can arrange nanoparticles into a specific pattern, and then, just by flipping a switch to turn the sound on or off, you can release them and rearrange them into a new pattern. This could let us build dynamic sensors for advanced optics, or maybe create incredibly sensitive detectors that can pick up on even a few molecules of a specific chemical.
So the potential here is obviously huge. But as with any brand new technology, there are still a few steps to go before you'll find this in every lab around the world.
Which brings us to the big question, right? Is this technology ready for prime time? Can scientists start using these acoustic tweezers tomorrow?
Well, not quite. See, this experiment was a proof of concept and it used these perfect uniform plastic beads. The next critical step is to try it with real biological samples, which are a lot messier and more varied. They also need to check how well it works when liquid is constantly flowing over the chip, and of course, test how durable and reusable these chips are.
But here's the key. These are engineering challenges, not fundamental roadblocks. The science works. So the long-term vision of having these standardized, off-the-shelf acoustic tools that labs and even factories can use, that is absolutely within reach.
In the end, I think this quote from the researchers just sums it up perfectly. What they've created is an elegant piece of engineering the sound. They aren't just making noise, they're sculpting it, they're shaping it into a tool to perform this incredibly delicate, precise work. It's a beautiful marriage of physics and engineering that could fundamentally change how we interact with the very building blocks of our world.